derivatives here. So we're going to be continuing to move through how we do these derivatives without having to use the definition of a derivative. So we're going to keep on kind of building in some more shortcuts. Today we're going to see two important shortcuts. So those two are called the product and quotient rules. So the product rule can be used if you have the product of two functions. So if I have like x times e to the x, those are two separate functions that I can't combine into the same kind. To deal with that, I'd have to use a product rule. However, if I had something like x times x squared, do I have to use a product rule to deal with this? X times x squared is just x cubed, and then I can just use my power property from last section to deal with that. So make sure before you get ready to implement the power property, you're not like, getting out a sledgehammer to try to squish an ant, right? That you're using the proper tool and you're not just like overdoing it. Although the the product property would be fine, it's a lot more work than you need to. So what the product property says, if I have the derivative of f of x times g of x, that's just going to be f times the derivative of g plus g times the derivative of f. So let's look at a couple of examples. So if I have f of x equals x e to the x, do we see that this is going to be the product of two functions, right? Where x is my f and e to the x is like my g, right? So if I apply the product property, I'm going to have f times the derivative of g plus g times the derivative of f. So far, so good. What is the derivative of e to the x? E to the x, that's correct. And what's the derivative of x? 1. So if I want to combine this, notice that each of these terms has a common factor of e to the x so I can write that maybe as e to the x times x plus 1. So far, so good. Part B says to find the nth derivative. How am I going to do that? Am I going to be able to do that directly? No. My plan would be, well, let's see what the second derivative is, and maybe the third derivative, and see if I can detect a pattern going on that relates the derivative number to the result, and see if I can reason something out that way. Because I can't take n derivatives, right? Since it's not a specific fixed value. So I'm going to be taking the derivative of that. So I have f times the derivative of g plus g times the derivative of f. Does everybody feel okay there? What's the derivative of x plus 1? Right, we're doing this. What's the derivative of x plus 1? Lucas, that's correct. He says 1. Feel free to answer. What's the derivative of e to the x? E to the x. And I notice here again that I have a greatest common factor of e to the x. So when I factor that out, I'd have e to the x times x plus 2. So far, so good. Do we see a pattern happening here so far? Maybe, maybe not. Let's do one more then. So again, f times the derivative of g plus g times the derivative of f. The derivative of x plus 2 is just 1. The derivative of e to the x is e to the x. When I factor that e to the x out and then combine some like terms, I have e to the x times x plus 3. And at this point, I would hope that we see the pattern. Right? The only thing that's changing is what we're adding to x. So if I asked you then, what would the nth derivative be? Well, it should be e to the x times x plus n. Everybody cool with how we did that? Again, I wasn't going to do it directly because I can't, right? So I'm just going to kind of just step through until I can see a pattern happening there. Okay, so let's look at our next example here. It says differentiate f of t equals square root t times the quantity a plus bt. Now, as this is currently written, I would have to use a product rule on this, right? But I think that's kind of overkill, because if I just distribute things through, what's square root t times t? T to the 3 halves, right? Because I have t to the first times t to the half, that'll give me t to the 3 halves. Do I need to use well, let's write this as t to the 1 half here. Do I have to use a product property now? No way, man. So let's not, right? What's the derivative of this a t to the 1 half plus b t to the 3 halves going to be? Can somebody tell me? Alex. Very good. Plus wonderful. Everybody agree with that? Again, could have tried to use the product rule here, would have ended up with the correct answer. I think a lot more work to get there. That was pretty simple. In general, this sort of technique is really important that you're picking up on in calculus. Most of what we're going to do in this class, there's like the hard way to do it, and then the sneaky way to do it, where I'm going to use some algebra to massage this thing into a form where it's like, now I can do this easily, versus like having to jump through a bunch of layers of properties to get to the answer. So looking for opportunities to, can I simplify this to just make it a power rule problem? Or can I simplify this so I can take out having to do an extra derivative rule? Those sorts of things will be really helpful for us. And in general, we need to begin to look for them all the time. Everybody's okay? All right. Bless you. All right, so let's say we have something that's a little less direct. It says f of x equals the square root of x times g. And we're told g of 4 is 2, g prime of 4 is 3, and we're asked to find f prime of 4. So let's just start by calculating f prime of x. So again, I'm just going to apply my product rule. So when the derivative of g is just g prime, right? Nothing more to do there. But what's the derivative of square root x? One half. There's probably some more to that though, right? One half x to the negative 1/2. Everybody's okay there? Okay. So if I do f prime of 4 then, I'm just plugging 4 in over here for x. Everybody feel good? Square root of 4 is 2. G prime of 4 is 3. That's given to me up here, right? G of 4 is 2. Again, that's given to me right there. And then what's 4 to the negative 1/2? Let's do 4 to the 1/2. That's 2. And then how about 2 to the negative 1? 1 over 2, and then times 1/2, 1/4. Everybody's okay with how we did that? Again, could you type that in your calculator? Of course you could. Not wrong to do that if you're like, ooh, I'm kind of shaky on that arithmetic. That's okay. Type it in your calculator. No biggie. So then we have 6 plus 1/2, or 6.5. How do we feel on that? No big deal, right? All right. So if we have the product of two functions, we have a rule for that. We also need a rule then for the quotient of two functions. That's the quotient property. So the quotient rule says we have the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. So again, instead of G's and F's, I think of bottom and top, because sometimes you might have something where we've named the function like, let's say g of x is equal to f of x over h of x or something. And now it's like, oh no, the letters are in the wrong space. Or even worse, where we've defined like h of x equals g of x divided by f of x. And now like, it's all confusing, the formula. I just think of bottoms and tops. Does that make sense to you guys? All right, so if we take a look at example 4, notice that this guy has no hope of me simplifying, right? There's nothing I'm going to be able to do to reduce that down or something to get where I don't have to use the quotient rule. Should be able to look at that pretty nicely and go, well, that's not going to reduce. Everybody agree? The x cubed plus 6 should be your dead ringer. That's not a sum of cubes, so the reducing there is not going to be productive for me. So again, this is like my top and this is like my bottom. So my derivative is going to be bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared Everybody so far so good with the initial setup? All right, let's do our derivatives. So what's the derivative of x squared plus x minus 2? 2x plus 1, thanks Violet. And then the derivative of x cubed plus 6. 3x squared. Is everybody okay? And I'm just choosing to write the derivative above so that I don't have to rewrite this thing like 100 times because it's like a lot of symbols to rewrite. That's the only reason I'm doing that. All right. Next up, I'm going to now FOIL this out so I can combine the like terms in the numerator. I'm not really ever going to FOIL out the denominator. Almost never would I want to do that because if there's any reducing to happen, denominator's got to be factored anyway, so I'm just going to leave that the way it is. So if I do a FOIL, I get 2x to the fourth plus x cubed plus 12x plus 6, then minus, I'm going to have 3x to the fourth minus 3x cubed plus 6x squared. Is everybody okay with how I like FOILed and distributed there? Kind of a hassle, but whatever. Now if we combine like terms, I have a negative x to the fourth, and I have a negative 2x cubed, and I have a 6x squared, and then I have a 12x, and I have a 6. Which parts did I FOIL? So I FOILed the two sets of parentheses that are multiplied together to get like that chunk. And then like I would have multiplied, or really just distributed to get that stuff. But I had to make sure I pushed the negative sign through. Does that feel good? Okay. So that gives me that. And I am not going to worry about trying to reduce that since it's a degree 4 polynomial. There's no obvious factoring to do there. I mean, I could try doing synthetic division or whatever, but like I'm not going to waste my time doing that. It's good enough. Does everybody agree? Just in case you're curious, it doesn't reduce. So, all right. Another example, it says find the equation of the tangent line to the curve e to the x divided by the quantity 1 plus x squared at the point 1, 1/2 e. So to write the equation for a line, I need a point and a slope. I have the point, right? What do I still need? The slope. How am I going to get it? The derivative, right? So to get that derivative, notice that's a quotient rule. So bottom times the derivative of the top minus the top times the derivative of the bottom all over bottom squared. Feel okay? The derivative of e to the x is e to the x. The derivative of 1 plus x squared is 2x. Very good. So far, so good. Now, could I simplify this? Sure. Do I want to bother with it though? Probably not, because I don't really need the derivative to do anything other than plug 1 into. So I'm just going to leave it in that messy form because all I'm doing is plugging in 1 anyway. I'd much rather deal with like combining constants than monkeying around with like foiling a bunch of stuff out and like factoring and simply like not even worth it. Everybody's okay? So I'm going to have 1 plus 1 squared e to the first minus e to the first times 2 times 1 over 1 plus 1 squared squared. So when I do that, I'm going to have 2e minus 2e over 4, or 0 over 4. Does that feel okay? So what's the equation for my line? Well, y minus y1 equals m times x minus x1, or just y equals 1/2 e. Was that nicer than trying to plug that stuff in and seeing what happened? Or, I'm sorry, then simplifying that down and then having to plug stuff in anyway afterwards? Like just plug it in. Once you got, if all you're going to do is plug a number into the derivative, don't bother simplifying. It usually just makes things worse, opens up an opportunity to make a silly algebra mistake. Just get the number in there as soon as you can. You know what I mean? And then it's whoop, smooth sailing. All right. So in summary, for what we've done so far, here are the derivative rules that we've gone through. Derivative constant, 0. We have the power rule, the derivative of e to the x, the constant property. If I take a constant times a function and I take the derivative, the constant just comes out front and I just do the derivative function. That's what this one is saying. That the derivative distributes. That's what that one's saying, across either addition or subtraction. Then this is the product rule and the quotient rule, just simplified down to like an easier looking statement that's less more compact or whatever. But that's the gist of it. This is the final topic that we're going to do before the next test. My plan for next week on Monday is we'll just do some practice on doing derivatives using these shortcuts. So I'll have a handout that we'll do some problems from. You guys can work together, can check them with me. I can show you some stuff on the calculator about how to check them yourself. Your calculator can't actually do the derivative for you, but if you have an answer, you can have it. There's a way to check it reasonably well with your calculator. I'll show you how to do that, which is super cool. And then Wednesday we'll do the review, talk about what the test format will look like and that kind of jazz. And then Friday is what I'm looking at for test day. Again, the test format is already up. So like talking about what to do. I have practice MC multiple choice questions. I'll get an answer key up in here fairly soon. And I have some free response questions that I pulled from the AP, also as exemplars that you can start working on at any point here in the next, 8 days before the test. Start picking away at that kind of stuff. It doesn't have to be all in one day. Do a little bit till you get like, ooh, I'm sick of this, my brain hurts. Move on to something else, or like, well, out of time today to do this. Move on to something else. Still be there tomorrow. But in general, starting early is usually a good idea. Do a little bit at a time. Tends to accumulate like a snowball If you do a little bit every day, you end up with a big old snowball by the end of the week without having to do like 6 hours at once to try to build your snowball, which is sometimes hard to find 6 hours at one time. You know what I mean? Any questions about what we did today or anything coming here in the not too distant future? Yes. Well, tomorrow's Friday, right? And then we have class Monday, Wednesday, Friday. So it's like a week from today is the test schedule. That's 8 days. You know what I mean? Like, because I want to have a day to just practice derivative rules, because like you got to be able to do those things like they are. And like, guys, just to emphasize this, so like these derivative rules here at the end that we have so far, this is stuff you like point blank have to have memorized. I'm not going to ask you to rewrite them, but you have to be able to use them in context. You got to know how to do them. Like there's no equation sheet. I'm not going to give them to you. You have to be able to do them in context. Finn?
What are the problems for
You mean the definition of a derivative?
Yeah.
So we'll see. The most common place something like that would come up. Let me see if I have a good example here in the multiple choice. I'll show you the most common way. So this is a kind of question that the AP would ask where you have to use the definition of the derivative, where it's like, here's a function, the derivative is which one of these limits. So like, that's a case where, yes, that definition of a derivative you have to have in order to do a question like this. Or they'll do reverse. They'll say, what is this limit? And then give you like 4 options, and you want to recognize that, oh, it's just asking me to do the derivative of the function. So I'm just taking my function and doing the derivative of that. So like, those are the 2 kinds of ways that typically the AP is going to ask you to use the definition of a derivative. If they ask you to differentiate something, I don't see a lot of like free response sections where they've asked you to use like the definition of a derivative to do it. So it's almost always just like use the shortcuts. We want you to use the shortcuts. Sometimes if you have to prove something, or like that's where the definition of the derivative comes in handy, or if you have like a graph where all of a sudden like the shortcuts are meaningless because you don't have a function, where you have to think about using that definition there. But it's most often going to be like something like this. I should look at the test format here. Yeah, I will not require you to use the limit definition of a derivative to find a derivative. However, you may need to use that definition to demonstrate like differentiability or something. If I ask, is this function differentiable at this value? The way you determine that is using that definition. So you need it to do something like that, but I would never ask you to like do this derivative using the definition, the limit definition. Does that make sense? So like we still have to have it, but it's not using it to do derivatives for the most part. Sure. Oh, you know what I forgot to ask even here, guys? Was did you guys have 3-1 homework questions? We didn't ask that at the start, did we? I just jumped right in. Really apologize. Do you guys want to take a moment and see if does anybody have homework questions from really anything so far, right? We've done, what is the test 2 is covering what? Sections 2.5 through 3.2. Plus that 2.1 in there, but that's a kind of a little wimpy guy. Basically, we're just doing slopes. We're okay? Okay. Didn't look very closely at this, or I would have had the practice sheet ready to go today in hand to you to start practicing on. Let's do it, and we'll do a couple. Okay? Good practice. this is a skill that like you really can't be bad at, right? Like we just have to be good at stuff like this. And it's one where ideally we have to be kind of fast at it, you know, like stuff that we can kind of, especially the early stuff we have to be able to do in our head. Actually, I'm going to leave that over here, and I'm going to drop them in at the end here. We'll just screen cap some stuff. That'll be easier. All right. Do you want to do? Let's have some fun. We'll call on some random individuals here to help us out. Yes. Aaron's like, oh dear. I was gone last class. I know, Aaron. I'm sorry. You can ask me questions if you're stuck. I promise. That goes for everybody else. Paul was like, I was gone for 2 classes, I think. I know, guys. All right, let's see. Random student generator. Random student. 4th hour. Reload roster. Violet, you're up first. So looking at number 1, we're just looking at taking the derivative. Yep, these are all just power rule problems here to start. You might have to do a little bit of cleanup for some of these later ones before you are ready to take the derivative. Like you might have some algebra to do before you are in a place where you can take the derivative. Not really the case on the first one here. So we'd write f prime of x equals
1 minus 2x to the second.
2x, 3x to the second. Perfect. Yes. Sure. So that's great. Again, like pretty straightforward, not much to do. Nate, you're next for, oh, he's in the bathroom. What a stinker. That's a pooping joke, by the way, when I said what a stinker. Because he was in the bathroom. It was like a twofer.
Okay.
Jacob, you are next. So before I start this, I would do a little bit of algebra to manipulate this thing to get into a better looking form. So how can I rewrite this x in the denominator? Can use a negative exponent there. And then x squared over 4 is really just the same thing as 1/4 x squared. And now if we think about it in this form, it might be a little bit easier to use our derivative rules as we've learned them, right? What do we get for the first one? So we're going to take this and multiply it to the front, and then subtract 1 from the exponent. That's the projector making that terrible squealing noise. Sorry. Shh. Can you do the next part then? Fantastic. Okay. It's the fan in the projector is squeaking. John Lewis. Is he here? Oh, okay. There's heads in the way. I couldn't tell if the empty desk was yours or someone else. Okay. Go ahead for number 3.
You'd rewrite that as is
Yes.
3 over x to the negative 1/2.
So 3x to the negative 1/2. Wonderful.
Then you multiply negative 1/2 by square, so it would be negative 3 over 2 minus x to the negative 3/2.
Wonderful. Okay. Let's see who's next. Charlie.
So cool, I missed like 3 classes. Now that you're not using them.
This one looks bad, but it's actually really easy. So you can do them one at a time. What's the derivative of x squared? So you need this one, right?
Yeah.
So if n is 2,
Yeah.
what am I going to get?
2x.
2x. Great. And then what am I going to do with the e squared?
Yeah, it's the e to the square.
Nope. It's not 2e to the 1 either. It's 0. Very good, Liam. Why is it 0?
Because I guess.
You guessed. Okay, that is the correct answer. Does anyone know why it's the correct answer? It's a constant. Yes, e squared is just a number, right? It's just a decimal, right? Like e is that like 2 point whatever, da 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 da. If I square that, it's just a decimal. It's just a number. It's not a variable. It's a constant. Derivative, shh. The derivative of any constant is just 0. So just 2x. That's all it is. No. If it was e to the x, if there's no variable attached to it, then the derivative is just, it's just derivative constant. Be like the derivative of 7, 0. Derivative of 1/2, 0. Derivative of e to the 6.2, 0. Derivative of square root of 7, 0. Constants. All right, let's see who's next. I know, guys, but this is good. This is good practice, right? Paulo, it's you.
So maybe x to 1/4.
Yes.
And then maybe 1/4 x. Negative 3/4.
Yes. Perfect. Good enough. Is everybody okay? Still feeling all right? Those of you that have been gone, this is some nice, like, working through some examples and seeing these rules in action. We're talking through what to do, I hope. If you are confused at what any of these answers come up to be, you feel free to stop and ask. Aaron. Oh, God. I wouldn't do that first, but you could. It does factor, but it's not going to be helpful here. But you do need to do some algebra to it before we want to take the derivative, or else you're stuck using the quotient rule. But you don't have to in this case. So the way it's currently written would require using the quotient rule. Now, there is some algebra we can do to avoid having to do that, which is what I would recommend here. So the trick is going to be, notice that the denominator is a monomial, right? It's a one term. So I can rewrite this as two fractions with a common denominator, right? What is x squared over x? What is x to the, or I'm sorry, 1 over x? That's what I would be trying to differentiate, is this guy. That's massively simpler, right? Okay, do you know the derivative of x? 1 is correct. Do you know the derivative of x to the negative 1? Negative 1 x to the, we're subtracting from the exponent, negative 2. Or just 1 plus x to the negative 2. What do you... So that trick of taking a monomial and like breaking it into common denominator fractions, that's a good one to remember. That'll come up again, maybe on like a test or something. Now you could always quotient rule it, but it stinks. You know, it's like a lot extra. And if you had to simplify your answer like in a multiple choice, yuckarooskies on the simplifying after doing the quotient rule on it. It's a bear, waste a bunch of time. The AP loves to give you the questions like this to have like a quick back door, especially on the multiple choice, that if you do it like the naive way, it's a time suck. But if you see the back door, it's like a 1-minute problem. That's what we're shooting for, is to get good at recognizing those back doors and make as many of these problems 1-minute problems as we can. The AP exam is timed. We want to save our time for when we really need it on questions that like, what the heck is this even asking? Versus something like, oh, this is just going to take forever. Usually there's a back door. They don't want you to make forever problems. All right. Yes, sir.
I have a college meeting right now.
Okay.
I need a pass.
That's okay.
I can bring one back.
I remember seeing your name on the list on the email this morning. You're fine. I'm not worried about it. Oh. Press the wrong thing. Yeah. All right. Who's going to be next? Who do we think it's going to be? Do you think it's going to be Michael Wiebelhaus, who just left? I accidentally had to restart my list, so we might get some repeated names. Oh, AJ was the next one. He stinks too. Elena's gone. Let's try it again. Michael! Corey. I wouldn't. You could, but I don't think it's going to help you. It's going to make it longer than it needs to be. I wouldn't do that. You could, but I wouldn't. I'm going to do the same trick that we did on the previous problem, because notice the denominator is a monomial, just one term, right? I would do that as my first step. How does 7x over 5 square root x, how does that reduce? What's x? Well, square root of x is the same as what exponent? Okay, so when we reduce, what do we do with the exponents? So we should have 7/5 x to the 1/2. Okay, same deal over here. So we're going to have 3/5 x to the 3/2. Now we're in a good spot to take our derivative. So what's the derivative of the first term going to give us? Perfect. Good. Again, seeing the algebra root to simplify that problem makes life enormously simple, right? Like if you can see the back door and recognize what to do, you know, smooth sailing the derivative is easy. Okay? In most cases, we're not going to have like monstrously difficult derivatives to do yet, right? It'll happen, but not for a while yet. There's almost always going to be a nice back door. Let's do some more. Oh, that's not the thing I wanted. That's what I want. Nope. I want this one. Absolutely. All right. Let's see. Who's gonna be next? Emily. Looking at 12. So how are you trying to do this right now?
I'm gonna FOIL it.
Okay. That's fine. So you have x cubed. Let's FOIL it out first for everybody so we can. So we'd have that, right?
Yeah. Plus x
Okay, so
minus 3x.
I said minus 3.
Oh.
But, yep. We did the FOIL.
Yeah. And then that'll be 3x squared
Mm-hmm.
plus 2x minus
Perfect. Wonderful. What would you have done if there was like a 3 there or something? Oh, I guess we can't do that yet. Never mind. Never mind. It would just suck. Eventually we'll find a shortcut around having to make it do these expansions. What else could we have done here to handle this problem though? Instead of foiling it out, what else could you do? You could do the product rule, right? Where you'd have x plus 1 times 2x plus x squared minus 3 times 1. And you'll end up with the same answer when you simplify down. Either way of going is fine. Let's see. In this case, I probably would have done what Emily did and not use the product rule. It seems pretty simple to FOIL that out, that I wouldn't worry about it. Maria. I mean, you can, but it's going to be, you still have to do the split anyways. It's just going to be like a wasted step. It's not wrong to do it, right? That's what Michael's initial thought was too. Not wrong to do that. It's just like running in place kind of thing, where you're not getting any closer to a form where we can do the derivative easy.
Okay, so it'd be the square root of x times the derivative of 3x squared plus 5x.
Okay, so we're going to do that. Okay, so you're doing the quotient rule, which is wonderful. You can absolutely do that here with this. So you have square root of x, and then that derivative of the top was
6x plus 5.
good. Minus,
Minus then 3x squared plus 5x.
and then derivative of square root x is x.
One x.
Good. And then the, yes, which just turns into x. So now we have to kind of like simplify this thing down, which is pretty yucky looking, right? So what would you want to do first to simplify this down? I hate this. That's the first thing I'd want to take care of. Right? Why do I hate this? It's like a fraction in the numerator, right? Because the negative exponent means like 1 over. So what I would do first, I suppose, is this. So when I multiply it here, that just turns into x, and I multiply it here, that just turns into 1. Now, you don't have to do it that way, but like, and in fact, let's make that 2. So it just nixes that 1/2 up there also. Does that feel okay? Then we would just distribute everything through and combine some like terms or whatever. Now that's not the approach that I would have recommended, although it's perfectly correct. No problem doing that. Michael?
So why did you multiply by
To get rid of the 1/2 here. I figured I just nix that fraction as long as I'm getting rid of fractions. Let's get rid of that one too. So what I would have done is I would have broken this into 2 fractions with a common denominator. And then when I take the derivative, boy, that's a lot simpler, right? So again, nothing wrong with what you did. It's a correct approach. It will get you the right answer. In a time setting, especially if the simplified answer, like it's a multiple choice with a simplified answer, where now you have to grind out that simplification, that's a lot more efficient to just take the derivative of 3x to the 3/2 plus 5 to the 1/2, like really quick to get an answer on that. So again, you didn't do anything wrong. There's a quick way to do it that we missed. And again, in a test setting for like class, probably didn't make it much of a difference, right? A right answer is a right answer. You have kind of a lot more time than typically, you need. But in the AP exam, where the multiple choice questions are like, like the no calculator or the calculator piece. I don't remember which one. One of the 2 sections is like 2 minutes a question. Is like the average you have to do things. So like doing the question that way, where it's going to spend like 3, 4, 5 minutes to grind through the simplification to figure out the right answer, if you can do all the simplification correctly, or we do it in like the 1 minute way. You know what I mean? So that's what I'm trying to emphasize, is also like, look for these back doors, look for these shortcuts. If I don't need to use the product rule or the quotient rule, I would like to avoid having to do that. Does that make sense? Okay. 14, let's see who's next on that one. You guys are doing a lovely job, though. Lots of good ideas. Addie. Okay. Yeah, you know what? I take this back. We're not doing 14. We can't do it right yet. There's a rule that we need that we don't have. So, Addie, you're going to look at 15 then. Same thing with 17. We can't do 17 yet. Yes. But is there anything you'd like to do before you start using the quotient rule? I would. And the reason I would is because if I don't, when I'm doing the quotient rule and I take the derivative of the top, I would then have to do a product rule inside of my quotient rule. Where if I don't have to do it that way, I prefer not to do it that way because it gets really messy when I have to nest like one of these rules inside of another rule inside of another rule. That gets complicated. My goal when I first look at the problem is, what can I do algebraically to make the calculus simpler? And I would do that. So what do we have? We have 5x to the fourth, and then we have negative 10, and then minus 3, so that's negative 13x squared plus 6 over x squared plus 2. Okay. So that's enough. So my derivative is going to be, do you remember the formula?
Isn't it the
Times the derivative of the top. Can you do that in your head?
try?
Yes, I love trying. Give it a shot.
Okay, would it be
So this number gets multiplied to the front,
okay, so 20,
and then we subtract 1 from the exponent. Do the next one for me.
negative 26, and then 1.
X to the first. Yep.
Um,
And what's the derivative of constant?
or 0.
0. Great memory. We just talked about it, right? And then we have the top. Yeah, give yourself a high five. That's worth celebrating. Do it. Okay, and then we have the top times the derivative of the bottom. What's the derivative of x squared plus 2?
It would 2, right?
2x,
Oh, yeah.
right? Because
Yeah.
we subtract 1 from the exponent. And then bottom squared. So far, so good. Now comes the yucky part. What's going to be the yucky part here? You got to FOIL all the numerator out and like combine our like terms and stuff. So there's no good shortcut way through this. It's just going to be kind of yucky. So let's see. We have 26x cubed and then, negative 26x cubed and positive 40x cubed. So that's going to be 14x cubed. And then minus 52x. And then we have minus 10x to the fifth minus 26x cubed plus 12x. You guys are all checking my work on these, right? Yeah, you're letting me down because I forgot to distribute the negative right there, but that's okay. I caught it. All right. So then we should have 10x to the fifth plus 40x cubed minus 64x all over this guy. And that's probably as good as we can do. Do you have your calculators with you?
Yes.
Pull your calculator out for a moment. Let's do this real quick. Because this is a problem that got, like the simplification got pretty messy, right? Let's show you guys how to check your answer. So to do this, what I'm going to do is I'm going to start by typing the original problem into the y equals menu. So in this case, I'm definitely doing like the fraction command. I'm doing alpha y equals, and then choosing option 1. That'll get the horizontal fraction bar in my calculator. So I can just type this in exactly like it looks like on my sheet of paper. Everybody okay there? Just typing it in. Next is what I'm going to do is I'm going to type in our answer that we just got. So alpha y equals. And you guys that have the color options, this one's, that's a nice option to have when you guys have the color calculators. Most of you guys, it looked like, had them. So that's our answer. And then what we want the calculator to do is to give us the graph of the derivative for what's in y1. So let me show you how to ask the calculator to do that for you. Everybody ready? So we're going to press the math button, and we're going to scroll down until we see the command n derive. So see command 8 is n derive. I'm going to pick that. So in that first blank, I'm differentiating with respect to x, because the variable in my calculator is x. The equation I want to differentiate is that equation y1, so I need to put the y1 there. So to get the y1, I press the vars button right there below the down arrow. I go over to y-vars. I pick function, and there's the y1. And then where it says x equals, I'm just going to type x. And I want to do one other quick thing before I hit graph here, is I'm going to turn off the graph for the first function because I don't actually care what the original problem looks like. I want to see what the derivatives look like and make sure the graphs match. So I'm just going to go and press enter on the equal sign for y1 so it's not highlighted anymore. And then I'm just going to graph this in a standard window. So I'm going to just hit zoom standard. So here's the graph of the derivative that we typed in. And right now the calculator's calculating the graph of the derivative of the original. And if I see this ends up being the exact same graph, I'm pretty convinced I did this correctly. If you have the color calculator, you'd see the new color draw over the previous one. It's a little bit easier to see what happened. Paulo? Sure. So you had all this into the calculator? Okay. Oh, so how to get the y1? Okay. So the y1, you just press the vars button under the down arrow. You go over to the y-vars tab. Yeah. So y1 was the original problem. y2 is my answer. And then y3 is going to be the derivative of the original. And I want to see if the calculator, when it calculates the graph of the derivative, gets the same graph as my answer. And if they're the same, then I'm convinced that I did the problem correctly. If they're different, I know that there's a mistake there somewhere. Hopefully, it's just a typo somewhere that I made, but x.
How do you get the y1?
Vars, and then go over to y-vars tab, and then you pick function, and then it's all the y's are there. Or again, if you wanted to, you could look at the table and compare y2s and y3s. Or if I look at those values, I notice that y2 and y3 are giving me the exact same values. More great evidence that my answer is the derivative. Does that, you guys get what I'm doing here with what this is doing? It's a wonderful check to have, right? If you have access to your calculator, you should know if any problem like this is correct or not, right? You can use it to check all of our homework along the way if we want to check something. Ooh, did I did that right or not? That's a really valuable resource to have. Now let's say that the y2 ended up being wrong, right? The thing that I got as my answer is wrong. The first thing I would do is try typing in my unsimplified answer to see if the mistake was when I took the derivative or was the mistake when I did the simplifying. So next, if my answer for y2, the one that I found was incorrect, I want to go back to the unsimplified derivative and check it against that one to make sure, did I make a mistake doing the calculus or did I make the mistake simplifying and doing algebra? Makes it easier to find what it is that I'm looking for. If I can say, okay, this first half was correct, the mistake was over here in the second half, or, oh, the first half was wrong, let me redo the calculus piece. You know what I mean? Like, that is enormously helpful in finding a mistake. Let's stop here for today. Sound good to hear, dudes and dudettes? All right. So we'll do some more practice on our derivative shortcuts on Monday. We'll do 3-2 homework quiz and questions and stuff, and then we'll just do some more derivatives practice.
3-2 won't be due now. It won't be due this Sunday.
Correct. So what's due this Sunday would have been like 2-8 and 3-1 or something. That sounds right. Okay.